In 2.3, we're going to compute limits without using tables or graphs. And actually from now on, we do not use tables and we do not use graphs to compute limits. So the first thing we're going to look at is we're going to look at a special case. And so this would be our first theorem, the limits of linear functions. So a linear function is of the form f of x is equal to mx plus b. Now the thing about lines are, and let's just draw some random line. They don't have any holes, they don't have any breaks in them. So let's just say I wanted to find the limit at some point. Well, I know I can come in from the right, and I can come in from the left, and there's no breaks, and actually it's defined at every point. So the way we compute the limit for a line is we're not going to do tables, we're not going to do graphs. What we're going to do is what I call plug and chug. And that's what we're going to be doing from now on when we evaluate limits. We're going to do a plug and chug, meaning whatever a value you're approaching, you're going to substitute that in for x. So it's just a substitution. In example 1, part A, we have f of x is equal to negative 3x plus 7. So if I was to evaluate that limit, it would be the limit. And here, what we're approaching is we're approaching x is equal to 5. So as x goes to 5, now I'm not going to put in f of x. I'm going to write down explicitly what my function is. So negative 3x plus 7. And now all I have to do is, since it is a linear function, it's just plug in 5 for x. Once I've plugged in 5 for x, I no longer use the limit notation because I've evaluated the limit. So it's going to be negative 3 times 5 plus 7. So negative 15 plus 7 would give me a negative 8. Now the next example B, that's a linear function as well. Because remember, this is equal to 0 times x plus 11. So if I was going to evaluate the limit, all I have to do is do the plug and chug. So this is going to be equal to the limit. Again, we're still approaching x is equal to 5 of 11, which is simply 11. So whenever you have a constant function, meaning there's no x in the expression, then it's equal to the function. Let's do one more. We're going to do the limit as x approaches 5 of x, and that's just simply 5. So again, this is the method we're going to do now when we do limits. We're not going to do tables, we're not going to do graphs. Remember, tables and graphs, they just give us a conjecture, a guess. Okay, we're going to plug and chug. So now this theorem just tells us some properties that we have when we have two functions whose limit does exist. So let's say we have some function f of x and another function g of x. And let's say the limit exists as x gets closer to a. Well, this first property just says that when you compute the limits and you're adding two functions, you can add the functions first and then do the limit, or you can do the limit of each and then add. So that's all of these 7 properties are doing. Combine the function first, then take the limit, or take the limit and then combine. So if we're subtracting the two functions, we can do the subtraction of the functions first and then take the limit, or break it up, do the limits first and then the subtraction. So property 3, constant multiple. if you have a function times some constant real number c, again, you can multiply by that constant real number, then take the limit, or take the limit of the function and then multiply it by the constant. And then we have our product. Multiply the two functions first, then take the limit, or take the limits and then multiply. Quotient. Divide the functions first, then take the limit, or take the limit, then divide. Okay, so we do have to be careful that our denominator is not equal to 0. And then our power rule says that if you're going to take a function to some power n, and n here is just going to be a positive integer, like 1, 2, 3, 4, and so on. So we can take the exponent first, then take the limit, or take the limit of the function and then the exponent. The last one is our root power. So just remember, we have to be careful when we're talking about roots. So we can take the root first or the limit first. So we have to be careful, because if we have an even root, like a 1/2, which is a square root, or a 1/4, which is the fourth root, that would mean n is even. Then as we approach our a value, we have to make sure that our f of x are always positive, so we don't get a negative underneath an even root. So going back to this power root and the quotient, or the power and the quotient. Remember, we were saying with linear functions we can do a plug and chug, but really, if we look at this quotient, if we take two linear functions and we make a fraction, what we have is a rational function. And we look at this power, if we take any linear function to some power or exponent n, what we've done is we've created polynomials. Which brings us to this direct substitution property. That's what your textbook will call it. Remember, I just call that plug and chug. Okay. Same thing. So the direct substitution property says that if you have a polynomial or a rational function, you can also do plug and chug, which means just take the a value and plug it in for the x value in your function. So let's look at the next slide. We're going to evaluate these limits, but we're going to do plug and chug. In part A, notice that x squared minus 3x plus 7 is a polynomial. So to evaluate this limit, all I have to do is plug in -1 for x. Now remember, once I've done that, I don't need that limit notation, because now I've evaluated the limit. So what we get is 1 plus 3 plus 7, or 11. Okay. And then part B, we have a rational expression. So we can go ahead and plug in 2. So you'll get 2 squared plus 5 over 2 minus 1, or 9 over 1, which is just 9. So it's much easier than making tables. The key is it has to be defined, so there's no holes or breaks. Part C, that's a polynomial. If I multiply it out, I'll get a polynomial. So again, all I'm going to do is plug in 1 for x and get 1 minus 2 times 1 plus 7. So we have -1 times 8, which gives us a -8. And then we'll do one last example with a root. So notice what's underneath the square root is a polynomial, and we're allowed to use plug and chug with polynomials. So this is just going to be the square root of 0 minus 0 plus 3, or the square root of 3. And so that's the basic idea to do a plug and chug. We do have to be careful. Sometimes when we plug in the a value that we're approaching, we may get something weird. So that would be our indeterminate forms. So this is just some of our indeterminate forms. There are much more. In this particular section, what you're going to be worried about here is the 0 over 0 case. All of these indeterminate forms mean that if we get that when we evaluate the limit, then we have to try something else. Indeterminate means cannot determine the limit. Okay? So 0 over 0 is not 0, and it's not undefined. It just means that you have to do something else to evaluate the limit. So in this particular example that I'm going to be doing, you have to remember your algebra. Super important here. Notice that if I were to plug in 4 in part A, I would get 0 over 0. Again, that just means I need to do something more to evaluate this limit. And that something more is not a table, it's not a graph. It's algebra, if you can do algebra. So notice in the denominator, I have the square root of x. So the first thing I think of is conjugate. Rationalize that denominator. So this is going to be the limit as x goes to 4 of x minus 4 times the square root of x plus 2, right? We want to keep everything the same. Since we had a subtraction, we do addition. Over the square root of x minus 2 times the square root of x plus 2. Notice if I were to evaluate this limit, it would still be 0 over 0. It's still an indeterminate form. I'm going to leave the numerator factored because I know something's going to cancel. And then I'm going to multiply out that denominator, which will end up being x minus 4. So notice this is still 0 over 0. As you're doing your algebra, you just want to, at every step, double check your limit. Just so that if you don't get an indeterminate form, you can stop. But notice that the x minus 4s are going to cancel. So now I'll have the limit as x goes to 4 of the square root of x plus 2. When I evaluate that limit, I don't get an indeterminate form. What I get is the square root of 4 plus 2, which is just equal to 4. So this is the case where you actually have a hole in the graph at 4. But remember, we can approach the limit. We never have to actually get there. Let's do another example where we have to do some algebra. In example B, if I were to evaluate that limit by plug and chug, so I'm going to put in -1 for x, I would get 0 over 0. I would get the indeterminate form, which again tells me I have to do some algebra if possible. When I look at this expression, what I notice is that I have a trinomial in the denominator. That tells me, why don't I try to factor the denominator? And if I were to factor that, it should go x minus 5, x plus 1. Oops. Pen's not working good, sorry. So notice again, this is still a 0 over 0. But now I can cancel the common x plus 1 to get the limit as x goes to -1 of 1 over x minus 5. Now when I evaluate that by plugging in -1 for x, I get 1 over -1 minus 5, or -1 over 6. So again, still much easier than making tables. Okay, let's look at one more example. So this might have been something that you forgot about, complex fractions. If I put in -1 for x, again I get 0 over 0. That tells me I need to do something else. So what I'm going to do is from algebra, I'm going to clear my fraction, the 1 over x, by just multiplying top and bottom by x. Now that's not the only way that you can simplify complex fractions, but it's usually the fastest way. So what I'm going to get in the numerator is 1 plus x. In the denominator, I think I'm going to leave it factored as x plus 1 times x. Again, the reason why is because I can see that the 1 plus x and x plus 1 will cancel. So I have the limit as x goes to -1 of 1 over x. And now plugging in -1 for x, my final limit is just going to be -1. So we looked at a case where we just plugged in and we got ourselves a number and we were done. And then we looked at a case where we plugged in for x and we got an indeterminate form, so we had to do something more. So in the next slide, we're going to look at another example where we get an indeterminate form. So notice in example 4, if I put in 1 for x, I get 0 over 0. The problem with this one, this particular example, is that there's nothing I can do. I can't just get rid of those absolute values. I have to go back to my definition of an absolute value. Remember, the absolute value is a piecewise function? It has two pieces. We can just drop the absolute values if what's inside the absolute values is greater than or equal to 0. Otherwise, if what's in the absolute value is negative, we take its negative, so we get a negative makes positive. So since the absolute values, to get rid of them, we have to split it up into two cases, the positive and negative. Then that's what I'm going to do with this limit. I have an indeterminate form. The thing is it's the absolute value that's messing me up. So I'm going to come in and do the limit from both sides. I'm going to approach one from the right and one from the left. So if I approach from the right, I'll have the limit as x approaches 1 with a plus to indicate from the right of x minus 1 over the absolute value of x minus 1. So this is what I'm going to be evaluating. If I'm coming in and I'm approaching 1 from the right, my x values are going to be larger than 1. So what's going to happen with this absolute value is it's always going to be positive. So to get rid of the absolute value, all I have to do is drop it. Notice I'm still writing my limit because I haven't evaluated my limit yet. So this is going to be x minus 1 over x minus 1. That's still indeterminate because if I put in 1, I get 0 over 0. But I can reduce that to be the limit as x goes to 1 from the right of just 1. And now the limit of a constant is the constant. And I'm not circling that 1 because that's really not my final answer. Remember, I'm supposed to figure out the limit as x goes to 1, not as x goes to 1 from the left and right. So now I'm going to come in from the left. So recall previously the limit exists if when you come in from the right and the left you get the same number. So let's see if I get 1. So it's x minus 1 over the absolute value of x minus 1. So now we have to think about this. If I come in from the left, I'm plugging in values for x that are less than 1. So what's in the absolute value is going to be negative. So to get rid of the absolute value, I need to take the negative of what's in there. So I'm going to have x minus 1 in the numerator, a negative in parentheses x minus 1. Again, that's still indeterminate. I still can't evaluate this limit until I reduce. So this is just going to be 1 over -1, or -1. So the limit as x goes to 1 from the left of -1 is equal to -1. All right, so what does all this mean? This is not enough work. Remember, the original thing that I was supposed to find was the limit as x goes to 1. So I need to make a conclusion. The limit as x goes to 1 of x minus 1 over the absolute value of x minus 1 does not exist. So I'm just writing D and E for does not exist, or you could do undefined. So let's just do a sketch of the graph. Remember, a graph is not a justification, but it's nice to see a picture sometimes. So if we look at 1, if I put in x values that are larger than 1, then I get this horizontal ray. It's not a line. And then if I look at the other part of the graph, it's going to look like this. So notice at 1 there's a big break. If I come in from the right, I approach 1. If I come in from the left, I approach -1. Let's do another example where we actually have to come in from both sides. And that would be any piecewise function. Example 5 has a piecewise function in 2 pieces. So I can't really figure out what the limit as x goes to 2 is unless I come in from the right and the left, because at 2 is when this function breaks up into 2 pieces. So if I come in from the right and I want to look at the limit as x approaches 2 from the right of f of x, since I'm dealing with a piecewise function, I have to specifically say what piece of the graph I'm using. So I can't just put f of x in there. So if I'm coming from the right, I'm looking at x values that are greater than 2. So I would use the square root of x minus 2. And now that I've written explicitly what part of my piecewise function I'm using, then I can plug in chug. So this is going to be the square root of 2 minus 2, which is the square root of 0, and that's just 0. Now let's come in from the left. If I'm coming in from the left, I'm looking at values that are smaller than 2, so I would be using x plus 1. Now I can actually plug into, notice when I just had f of x, the general f of x form, I couldn't really plug in 2. It's like, what are you plugging it into? So now this would be 2 plus 1, which is 3. All right, so in part C, the limit as x goes to 2 of our function f of x does not exist. And that would be from part A and B. Since those 2 values are different, the limit does not exist. The last thing we're going to look at in this section is we're going to look at what happens if you can't do algebra, or if coming in from the right and left really doesn't work. So first what we're going to do is we're going to look at this preliminary theorem that is really simple. It says if one function is less than or equal to another function, then their limits will have that same property. So if f is less than or equal to g, then the limit of f is going to be less than or equal to the limit of g. Okay, and here we're just assuming that we're looking at as x goes to some a, so near some a value. However, that theorem's going to give us what we call the squeeze theorem. So the squeeze theorem we use if coming in from both sides doesn't work, or algebra doesn't work, and we get this weird form that we can't work with. So let's say we have 3 functions, f, g, and h. Let's just say that f is less than or equal to g, which is less than or equal to h. So g is between f and h, but just near that a that we're approaching. Maybe they're not, we don't have that relationship for all values. Okay? So let's just say when we take the limit of f and the limit of h, it's the same. Okay? Then that's going to force the limit of g to be the same, because g is between them. Example 6 gives you tangent of x over x. And let's say that we're approaching 0. So near 0, tangent of x over x is going to be greater than or equal to 1, less than or equal to x squared plus 1. So we want to compute the limit as x goes to 0 of tangent of x over x. And the problem with this is it's indeterminate. If you put in 0 for x, tangent of 0 is 0, and then you have 0 in the denominator. Okay, but when I look at this, there's nothing I can do algebraically, and I can't come in from both sides, because when I come in from both sides, I'm going to get some real funky answer. Okay? So what I'm going to do is I'm going to use this squeeze theorem. I'm going to take the limit of all three pieces, and so this is how I'm going to write it. I'm going to take the limit, and here we're approaching 0, so as x goes to 0 of 1, and that will have to be less than or equal to the limit as x goes to 0 of tangent of x over x, which needs to be less than or equal to the limit as x goes to 0 of x squared plus 1. So all I did was take the limit as x goes to 0 on all three pieces of my inequality, and I can do that from the first theorem we looked at. When I evaluate the limit as x goes to 0 of 1, it's just going to be 1. Now notice I'm going to keep the limit as x goes to 0 of tangent of x over x, because that's what I'm trying to find, but it's indeterminate. Now the limit as x goes to 0 of x squared plus 1 is also 1. So think about what that says. It says the limit has to be greater than 1, greater than or equal to 1, and less than or equal to 1. And the only way that can happen is if the limit is equal to 1. So I wouldn't stop with the inequality, because remember, we were supposed to find the limit as x goes to 0 of tangent of x over x. Oops. Erase. It's equal to 1, because that's what the other two are. Okay? So the limit is equal to 1, but I have to justify that. So I would just write by squeeze theorem. Alright? So that's the idea. You just take the limit in the inequality itself and see what happens. Example 7 is our last example of this section. It says that we have to use the squeeze theorem. In order to use the squeeze theorem, I have to have an inequality. I'm supposed to show that the limit as x goes to 0 of x squared times cosine of 1 over x is equal to 0. However, if we look at this, and I plug in 0, I get 0 times cosine of 1 over 0. The problem with that is I don't know what the 1 over 0 is, because that's undefined. So what is cosine of undefined? Who knows? So this is a case where we get some weird form that we don't know what to do with it. The problem with this, again, is I wasn't given an inequality. So to use the squeeze theorem, I have to have an inequality. So what I'm going to do is I'm going to ignore the x squared, and I'm going to build myself an inequality. So notice we have a trig function, cosine of 1 over x. And typically with the squeeze theorem, we get a lot of trig functions mixed in with other functions. So remember from trig that cosine, it doesn't really matter that the argument is 1 over x. Cosine is always less than or equal to 1, greater than or equal to negative 1. So I've created this inequality. Now all I have to do is build it up so it looks like x squared times cosine of 1 over x. So all I have to do is multiply all three pieces by x squared. You do have to be careful though, because remember, whenever you multiply or divide by a negative number, you have to flip your inequality. However, I don't have to worry about it in this case because it's an x squared. So x squared is never negative. So if I multiply all three pieces by x squared, I get negative x squared less than or equal to x squared cosine of 1 over x less than or equal to x squared. So now I have my inequality so that I can use the squeeze theorem. Again, all I did was build up from my cosine function. So we're supposed to be taking the limit as x goes to 0, so I'll do that on all three pieces. So the limit as x goes to 0 of x squared times cosine of 1 over x less than or equal to the limit as x goes to 0 of x squared. It's like my pen tip is wearing out. So plugging in 0, I have 0 less than or equal to the limit as x goes to 0 of x squared cosine of 1 over x, which is less than or equal to 0. So since the left and right are both 0, then that means that the limit as x goes to 0 of x squared times cosine of 1 over x is equal to 0 by squeeze theorem. Okay, so again, no more tables, no more graphs. If you want to figure out what a limit is, you have to plug and chug and get a number. If you don't, if you get an indeterminate form, try algebra. If that doesn't work, come in from the left and the right. If that doesn't work, you might have to use the squeeze theorem. Okay, so that's it for this section 2.3.